Okay, so we're going to have a look at another question from the topic of electromagnetism. We're told an alpha particle enters a uniform vertical electric field at an angle of 30 degrees to the field. The field, we're told, points up and has a field strength of 30 volts per meter. We're told the alpha particle's initial speed is 150 kilometers a second. We're asked A, to draw a diagram, B, calculate velocity after 5 seconds. All right. So in this question, there's a few things we have to assume. First, we'll draw our diagram. So we'll draw two parallel plates because this gives us a good template for what the field looks like. So if the field goes up, that means the negative charge is at the top and then the positive charge is at the bottom. So we have negative at the top, positive at the bottom. That means the field lines going this way all go up. So up, up, up. So this is what it means for the field to point up. We're told the field strength is 30 volts per meter. Now, a particle enters this field at an angle of 30 degrees to the field. This angle of 30 degrees to the field warrants an assumption. You could assume that it enters 30 degrees down. You could assume it enters 30 degrees up. So this could be 30, this could be 30. We're going to assume it's 30 degrees up. That is the more likely meaning of this particular wording. So we have a particle, it enters a field, it's coming in sort of this way so that this angle is 30 degrees. We're told it has initial speed 150 kilometers a second, 150 kilometers per second. We're told the field strength E is 30 volts per meter. So this is pretty much what the setup looks like. We have a particle entering a field. It's entering a field at an angle. The field strength is 30 volts per meter. This is pretty much what we want. We could add to this a trajectory if we would like. We do know that this is an alpha particle. So for an alpha particle, we need to know the charge and we need to know the mass. So the charge of an alpha particle is about 3.2 times 10 to the minus 19 coulombs. And the mass of an alpha particle is about 6.6 times 10 to the minus 27 kilograms. So this is positively charged. Given that the positive particles, that the positive bar is down the bottom, if a field is going up, essentially the positives are at the bottom is going to repel the particle. So it's going to enter with a sort of diagonal velocity this way, but then it's going to curve parabolically towards the negative. So the trajectory will be something like this. That's the sort of shape that we should expect. So this is the answer to part A. So part B says calculate the velocity after 5 seconds. All right. So we're going to do this as a particular type of problem. We're going to set up the accelerations, then find the velocities, then find the positions. So if we have a look at our diagram, it's going to be going, we'll choose our x and y axes. We'll choose x to go this way, we'll choose y to go this way. So we have acceleration in x is equal to, and acceleration in y is equal to. In this problem, we've not been told anything about gravity. So for the purpose of this problem, we are going to assume that there is no gravity. We're going to assume the only force we want to calculate is the field. This is a sort of isolated type of problem. Often these problems will involve gravity because the particle has mass, so it will be affected by gravity if it's on the surface of the Earth. In this question, we're not going to bother with gravity. We're just going to bother with the field. So we need the acceleration on the particle due to the field. And then we need to break it up into its two piecewise components because part of it is... then we'll need the initial velocities from the diagram. So the acceleration from the field will only be towards the negative. This will be the acceleration due to the field. So the acceleration due to the field is going to be, we have a formula for the acceleration due to the field. We know ma is equal to qe. This tells us the acceleration is q times e divided by m. So charge times field divided by mass. The charge on the particle is 3.2 times 10 to the minus 19. The field strength is 30. Then the mass of the particle is 6.6 times 10 to the minus 27. And this acceleration will only happen in the positive y direction. So whatever number this is, it's positive ay. This will be the value for ay. Ax will be 0 in this case. There is no acceleration in the x direction. There is initial velocity in the x direction though. So let's find our acceleration in y. It's going to be 3.2 times 10 to the minus 19 times 30, which is the field strength, divided by 6.6 times 10 to the minus 27. My calculator tells me that's 1.45454545 times 10 to the 9. So we're just going to round that. We're going to say that's 1.45 times 10 to the 9. 0.45 times 10 to the 9. It's 3 significant figures, but it's just an approximation anyway. So these are our initial accelerations. 0 in the x direction, 1.45 times 10 to the 9 in the y direction. So the velocities we can get from this, the velocity of x is the velocity initial in x. The velocity in y is 1.45 times 10 to the 9 times time, plus the velocity initial in y. Now, we do have velocity initial in x and velocity initial in y, and we can calculate them from the fact that this enters at a 30-degree angle. So let's draw a little vector diagram to get these. This is 150 kilometers per second. So that's 1.5 times 10 squared kilometers per second. So that's 1.5 times 10 to the 5 meters per second. It has a component in the x direction, a component in the y direction. This is 30. So this is VIY. This is VIX. We can use sine and cos to find this. So we know sine of 30 is equal to opposite over hypotenuse. That's VIY over 1.5 times 10 to the 5. This tells us that VIY is equal to 1.5 times 10 to the 5 times sine 30. 1.5 times 10 to the power of 5 times sine 30. My calculator tells me this is 7.5 times 10 to the 4. 5 times 10 to the 4. So this means our velocity initial in y is 7.5 times 10 to the 4. It's 1.45. 1.45 times 10 to the 9 times time plus 7.5 times 10 to the 4. And then the velocity in x we get from using cosine. So we've got cosine of 30 is equal to VIX. This is adjacent of hypotenuse over 1.5 times 10 to the 5. So this tells us that VIX is equal to 1.5 times 10 to the 5 times cosine 30. 5 times 10 to the power of 5 times cosine 30. This is 1.299038 times 10 to the 5. So let's say 1.3 times 10 to the 5. 3 times 10 to the 5 approximately. These are just approximates, but that's good enough. So the velocity initial in x is 1.3 times 10 to the 5. So we have the accelerations. We have the velocities. The question actually tells us to calculate the velocity after 5 seconds. We don't need to do the positions in this case. You could also do the positions here because you find accelerations, then velocities, then positions. We don't need the positions. We just need the velocities. So if t is 5, this implies the velocity in x is 1.3 times 10 to the 5. It's just a constant value. And v of y, we're going to let this t equal 5. So we get 1.45 times 10 to the power of 9 times 5 plus, this will be 7.5 times 10 to the 4. 5 times 10 to the 4. This is 7.25 times 10 to the 9. 7.25 times 10 to the 9. So these are the velocities in terms of meters per second. Very, very gigantic velocities. So now if we want the overall velocity, we need to do the square root of the sum of squares, because one of these is in x, one of these is in y. So if we draw a little diagram, the overall velocity has a y, 7.25 times 10 to the 9, has an x component, 1.3 times 10 to the 5. So this is the overall velocity. So v is the square root of v in x squared plus v in y squared. This is the square root of v in x, which is 1.3 times 10 to the 5 squared, plus v of y, which is 7.25 times 10 to the 9 squared. These are comically large numbers, but that's fine, because if you do the working right, the answer will be right. If you do the working wrong, your answer might be wrong, but if you do the working right, your answer will be right. So trust your working, and think about the numbers once you've got your final answers. So 1.3 times 10 to the 5 squared plus 7.25 times 10 to the 9 squared, the square root of all that is still 7.25 times 10 to the 9. So this is 7.25 times 10 to the 9. This makes sense. This term is way, way bigger than the other term, and this is meters per second. So the velocity that we're getting in this question in terms of meters per second is absolutely gigantic, right? This is an incredible velocity. It's pretty essentially impossible because it's larger than light speed. So unless particles travel faster than light speed, which is possible, but not in the standard physics framework, this is the answer. But certainly this is the answer that we're able to calculate. So when we went through this question, we set up what it was that we were going to find. We tried to find the acceleration from the field. This was based on the strength of the field, the charge of the particle, and then the mass. We then identified based on that what direction it was going to travel. Once we'd found that acceleration, we identified in which direction that acceleration was going, set it up in our ax and ay equations. From the accelerations got the velocities, and then we used those velocities to evaluate the velocity when time is equal to 3. So this is quite a messy question, but it's not particularly hard algebra. It's just the physics is a little bit messy to set up. So be careful when you're working with numbers like these.